This is a video to review derivatives and integrals for Mechanics C for physics. We start with some displacement time data for an object that is moving, and it's listed here in this chart. We put it on a spreadsheet, and it looks like a nice parabola here. So we are suspecting that it's probably a polynomial of order 2. We can then use the spreadsheet or our calculators to determine the line of best fit through that. And now we'll go to calculate on this data. So our graph is a displacement versus time. So this is S is for displacement. The line is best fit gives us an S sub t. And again, that subscript t means it's based on time. Is negative 5.4 t squared plus 23.3 t plus 12. Now 12 is our beginning displacement, so if I put 0 in for time, I'll get 12. Now we want to take the first derivative of this equation, so we're taking the derivative of displacement with respect to t, and of course we're using the power rule, so that gives us negative 10.8 t plus 23.3. Now our equation is a v sub t, so in other words, again, we're based on time, so this is velocity sub time, equals negative 10.8 t plus 23.3. And if we put 0 in for time, we have a beginning velocity of 23.3. And of course, that would be meters per second. Now, what if we wanted to find the velocity at 0.5 seconds? Well, we can use the limit theory and understand that the slope of tangent lines gives us instantaneous velocity, or we can simply use the equation. So we want to determine the velocity at 0.5 seconds. So what are we really doing there? We're saying the limit of the change in displacement with respect to change in time of our original function as delta t approaches 0. That's the same as taking the slope of the tangent line, okay, at 0.5 seconds. So we go back to our original graph. If I draw a tangent line at my 0.5 seconds, here's where I want to find the velocity at this particular time interval. The slope of the tangent line would equal the instantaneous velocity at 0.5 seconds. Okay, I've got that calculated out. The instantaneous velocity is 17.9 meters per second. Now I just simply used my graphing calculator and then did a dy over dx, and then once I graphed it, and I put in 0.5 seconds. And that's the slope of the tangent line. Okay, now what else can we do? Well, again, we have an equation where we derive for velocity sub time. So this is an equation of all of the slopes of tangent lines of that graph, or in other words, this is an equation to get all of the instantaneous velocities versus time. So what I do is I plug in 0.5 seconds where I see t here, and I just solve it, and I get 17.9 meters per second. All right, let's continue. Well, now we can take the second derivative of that equation, and we can get the instantaneous acceleration at any given time. Well, we've got dv dt, that would be the next derivative, the second derivative, and that just gives us a negative 10.8 meters per second. So the acceleration is negative 10.8 meters per second. How do we get that? Well, we're going to use the power rule one more time on the v sub t equation, and we see that is a constant negative acceleration. Now that makes sense because we have a concave downwards. You might be familiar with the second derivative test. If the second derivative is negative, then you're concave downwards. If the second derivative is positive, then it's concave upwards. Well, I like to think about calculus in terms of physics because it does help us see that the acceleration of this object is negative. Therefore, it travels away from the origin in a positive direction, but now it's starting to come back towards our origin, moving in a negative direction. So the graph really shows, why that's concave that way. Or again, you can think of it as finding the slope of the tangent line, okay, to the graph. So the limit of delta v over delta t of our velocity equation as delta t approaches 0. And the acceleration is negative 10.8 meters per second squared. Now, the instantaneous acceleration happens to be constant everywhere. Let's take a look at our graphs just to kind of reinforce this concept. So here's our velocity time graph. It is a constant line with a negative slope, and we see that everywhere we have a negative slope, and it's always the same. So what are our critical values? Well, our critical value is 23.3 is our beginning velocity. I want to figure out where it cuts the x-axis. That would be where velocity is 0. So I take my first derivative and set it equal to 0. So this is our velocity equation. So I've got negative 10.8 plus 23.3, and there should be a little t variable here. And I'm going to solve for t. So take 23 to the other side and divide by 10.8. I get 2.2 seconds. So then I place that on my graph, 2.2. And I take my graph all the way down to where it would be negative 23.3. Now I know that's going to be at 4.4 seconds, assuming that there's no air resistance to this. If it takes 2.2 seconds to get to here, then it's going to take another 2.2 seconds, okay, to get to negative 23.3. So our critical point here would be 4.4. Now that 0 is going to tell us we have a maximum. In this case, we're concave downwards. So somewhere around here is going to be our maximum displacement. So we have a positive slopes here. We'll have a 0 slope somewhere at the top here, and then we'll have negative slopes going down there. So where the slope is 0, that's where velocity is 0. That's where our maximum displacement is going to be. So it should be somewhere around 37 meters. Let's go take a look at the math here. So I know at 2.2 seconds, that's where velocity is 0. So then what I do is I take that 2.2, I plug it into my displacement equation, and I'm calling this S sub max. So I substitute that in, and it's 37 meters, within rounding differences. So there you go. And of course, we can look at the acceleration versus time graph. It's a constant slope of negative 10.8, always going in this direction here. So it's a flat line everywhere. So that is our differentiation. Now looking at integration, it's the opposite. We're going to take the antiderivatives here. But before we do that, let's take a look at our constants here. We know beginning displacement is 12 meters. We know beginning velocity is 23.3 meters per second, and we know that we have a constant acceleration of 10.8 meters per second squared. Okay, now when we start integration, of course, is the area under the curve. So we want to determine the velocity at 2.2 seconds. So we're going to take the area under our acceleration versus time graph. And if we quickly go back to see what that looks like, we're going to be taking the area of a box. Okay, 2.2 seconds is right here. If you can imagine, this is a box here. We're just simply going to take the area underneath that curve. So let's go ahead and do that. The area of the curve would be negative 10.8 meters per second squared. That's our constant acceleration value multiplied by 2.2 seconds. And we see that meters per second squared, 1 second crosses off the second squared, and we're left with negative 23 meters per second. Now that's the total velocity change during the time interval from 0 to 2.2 seconds. We have to remember that we were going 23 meters per second initially, now plus a minus 23, because that's the change that occurs during out that interval from 0 to 2.2. That gives us 0 meters per second. And that's right on target with what we saw already when we looked at solving for when velocity was equal to 0. Okay, now what about doing it by integration, algebraically, I suppose you wish to call it that. Well, acceleration is negative 10.8 meters per second squared. Now, acceleration, A, that letter is not integratable. So we need to write that as a differential expression. So what is acceleration in differential expression? That's dv over dt. Of course, that equals negative 10.8. Well, now we need to separate our variables. Our variables are together, so we cannot integrate that. Okay, so to separate our variables, I'm going to say dv. Okay, I'm going to take the dt to the other side and multiply that out. So I'm going to integrate the left side from 0 to v, dv, equals, now I'm doing 0 to 2.2 seconds of this right side here. So I'm going to integrate it. I'm going to get what's called a definite integral. The antiderivative of dv is just v, and the antiderivative of dt, of course, is t. So I have a definite integral from 0 to v here, and 0 to 2.2 here. So there we go. So I have v, I'm going to plug v in, and I'm going to subtract 0, because I plug in v first, and I subtract when I put 0 in. Okay, now I'm going to put 2.2 in, so a negative 10.8 times 2.2. Now I'm going to subtract, okay, from this one here, a 10.8, okay, multiplied by 0. Okay, and that's going to give me a final answer of negative 23 meters per second. Now again, that's from 0 to v. We have to remember that our beginning velocity indeed was 23. So 23 minus 23 once again gives us 0. So by the definite integral method, we see that it agrees with the area under the curve. Okay, now what's this plus c all about? Well, that is a constant. Okay, we know what that constant actually is, though. Okay, that constant is our beginning velocity. So this is a definite integral. I know that the c, of course, will subtract off because I'm going to have a plus c here, and I'll have a minus c here, and that's going to cross off. Let's take a look at our equation, okay, with doing an indefinite integral. So we integrate dv, and again, a negative 10.8 dt. When we take the integral of this, it looks like this. We just get a v equals negative 10.8 t plus our constant c. Now what are we doing here? We're doing an indefinite integral. We're just integrating both variables. Again, we're taking the antiderivative of dv to get a v, and the antiderivative of dt is just t. And this is our equation. Now, c, of course, for this is our beginning velocity, and we know that. Beginning velocity is 23.3, so I can just plug that in there. And this is my velocity equation. Okay, now what if I want to know the displacement from 0 to 2.2 seconds? Well, I'm going to need to take a look at my expression here. V can be written as ds dt. This, of course, is our differential expression. Then we need to separate the variables. We're going to have to take dt to the other side. And we're going to integrate this. Again, we're going to do a definite integral here. I'm doing a definite integral from 0 to s of ds, and from 0 to 2.2 of our velocity equation, k times dt. Now I got to think antiderivative. The antiderivative of ds is just s under the definite integral from 0 to s equals the antiderivative of this one is going to be negative 5.4 t squared plus 23.t plus c again, but we're doing a definite integral from 0 to 2.2, and I know that my c will subtract off. Now what am I going to do here? On the left side, of course, I'm going to put s in initially, and then I'll put 0 in initially, and those two get subtracted. I'm going to put 2.2 in for my first expression here. Notice I'm not including the c again because then it's going to become 0. And I'll subtract when I put 0 in for this expression. So I put in 2.2 for t here and there, and I'll place it there. I'm going to subtract the next one where I put 0 in. Okay, and it's going to come out to be 25.1 meters once I'm done. So our s is equal to that. But I have to remember my beginning displacement was 12, and I add that to get 37. Now again, this 25.1 is the change in displacement. okay, from 0 to 2.2 seconds. Now, if we do this by area method, okay, I can compare. All right, I'm going to, let's go back to our original graph for this. It's going to take me a bit to get back to it. Here we go. So I need the area under the curve here now. Notice how it's always bound by the x-axis. So this is just a triangle, 1/2 base times height, 1/2 2.2 times 23.3. Okay, let's scroll back down here. So I take 1/2 2 times 23.3, I get 25. And then I have to remember again, my beginning displacement was 12, so we get excellent agreement at 37. Now, of course, I've done some rounding. I might have done a little bit more rounding than usual. But we see that derivatives are the same as instantaneous slopes. And we see that integration is the area under the curve. We have to remember that when we're doing integration, we have to take the antiderivatives of this, right? In order to make that possible. Okay, now if I wanted to derive my displacement equation for this, okay, let's go back to this right here. I've got 5.4 t squared plus 23.3 t and plus c again. I know c is 12, so I could just put 12 in here. So without doing a definite integral again, I can derive the actual displacement equation by simply putting in my beginning constants value, which we know because we know our beginning displacement was. And then I don't have to do a definite integral from there. Okay, we will build more of this on class. I've got an example that I want you, okay, to try.